Good morning to all. My name is Rani, working as Assistant Professor in AC Department of Guntur Engineering College. Today I am going to discuss about CMOS inverter behavior when we are connecting with the resistor load. So this is the last characteristic in steady state electrical behavior. So if this CMOS circuit is connected to the resistor load, how the CMOS inverter is going to work. So in this section, I am going to explain. So for this section, I am converting the CMOS inverter into resistive model. So that means PMOS transistor offers some resistance. That PMOS transistor is denoted with the internal resistance of RP, and the NMOS transistor offer its some resistance. That internal resistance of NMOS transistor is denoted with the RB, and I am connecting the load resistors with 1 kilo ohm and 2 kilo ohms. So, and if you observe this circuit, so this circuit is going to convert it into Thevenin's equivalent circuit. So, at this point, PMOS, this 1 kilo ohm and 2 kilo ohms are connected in parallel. So, to convert this circuit into the Thevenin's equivalent circuit, we need to calculate the Thevenin's voltage and the Thevenin's resistance. So, Thevenin's resistance means the equivalent resistance of this circuit. So, if you observe this point, these two resistors in parallel connection, hence Thevenin's resistance can be obtained by parallel combination of this 1 kilo ohm and 2 kilo ohms. So if you take this 1 kilo ohm to kilo ohms parallel combination, so we can get the Thevenin's equivalent voltage as a 667 ohms. Similarly, if you get this Thevenin's voltage, so how we can get the Thevenin's voltage? So voltage across this 2 kilo ohms resistors. So how we can get 2 kilo ohms? So the supply voltage for this 2 kilo ohms is 5 volts. That's why voltage across this resistor is 5 into 2k by total resistance is 1k plus 2k. So like this we can get Thevenin's voltage. So Thevenin's voltage we can get 2 kilo ohms by 1 kilo ohm plus 2 kilo ohms into 5 volts, which gets results in 3.3 volts. So like this we can get Thevenin's resistance and Thevenin's voltage. By replacing this Thevenin's voltage and the Thevenin's resistance, we can get the circuit behavior like this. So before going to explain this circuit operation, so I want to give some introduction for this circuit. So if PMOS transistor are on, what happens PMOS transistor on? So PMOS transistor offer low resistance and NMOS transistor offer high resistance. So the low resistance offered by this PMOS transistor I am considering as a 200 ohms, and the high resistance offered by the NMOS or PMOS I am considering as greater than 1 micro. And if PMOS transistor off, NMOS transistor will be on. So in this case, NMOS transistor offers low resistance and PMOS transistor offer high resistance. So the NMOS resistor offer the low resistance of order of 100 ohms. Why I am taking here as 100 ohms? So if you observe carefully, NMOS devices offers low resistance than PMOS devices. Why? Because so NMOS transistors have the majority carries electrons. Those electron has a high mobility when comparing with the hole mobility. That's why NMOS devices naturally offer low resistance than PMOS devices. So that's why I'm taking this NMOS low resistance as 100 ohms and PMOS low resistance as 200 ohms. Let's see. So for the inverter, I'm giving the high input. What happens if you give the high input? Output will be low. That means if you give 5 volts here, so output must be 5 volts. But in this case, we are connecting the load resistors. So because of that load resistance, it loses some voltage. So how much output voltage we are getting here. So for high input, what happens? PMOS transistor will be off and NMOS transistor will be on. So hence NMOS transistor offer low resistance, that is I am taking as 100 ohms, and PMOS transistor offer high resistance, that is considered as greater than 1 mega ohm. So output to voltage, where we are getting the voltage across this resistor. So the voltage across this resistor, how we can get so this voltage we can get VTH into 100 ohms by total resistance 100 plus 667. So the voltage supply for this is only this one only 3.3 volts. The supply voltage is not coming here. So that's why Thevenin's voltage only the voltage across this resistor supply voltage is 3.3 volts into voltage across this resistor, hence I am putting 100, and the total resistance 100 plus 667 gives the output voltage 0.43 volts. Similarly, we can calculate the low input. For the low input, what happens? PMOS transistor will be on and NMOS transistor will be off. Hence, NMOS transistor offer high resistance of order greater than 1 mega ohm, and PMOS transistor offer low resistance of order 200 ohms. So now I have to calculate the output voltage. So for this output voltage, I am calculating the 3.3 volts plus voltage across this is 667 resistor. So voltage across this 667 resistor 5 minus 3.3 by total resistance of 200 plus 667. Like this we can get the output voltage. So the output voltage is equal to 3.3 plus supply voltage 5 volts minus 3.3 into voltage across this resistor 667 by total resistance 200 plus 667 gives 4.61 volts. So for resistor, because of resistor load, we are getting the output voltage as 4.61 instead of 5 volts. Like this we can calculate the output voltages and input voltages. Now I am going to discuss about the sink current and sourcing current. So when the PMOS transistor is off condition, when PMOS transistor is off, then the current flows from the supply to the load, from the load to output, output to the NMOS transistor, and then it goes to the ground. So this part of current is known as the sinking current. So that means we can define sinking current as the current flows from supply to the load, load to the output, and to the device to the output. Then such current is known as the sinking current. So a device output is set to sink current when current flows from the power supply through load and through the device output to the ground. Then it is said to be sink current. Then coming to the sourcing current, the current flows from supply to the output. From the output, it is goes to the load and then it is going to the ground. So this type of current flowing is known as sourcing current. So now we can define sourcing current as the output current said to be source current when the current flows from the power supply out of the device output and through the load to the ground. Then that such a current is known as the sourcing current. So like this, we can give the source current and sink current and how the circuit is behavior for the low input and a high input CMOS inverter. So I have explained it in this section. So thank you so much.